everybody, welcome back to Quantitative Reasoning. Today we are finishing up Chapter 8, which is our personal finance chapter, and we are going to be looking at Section 8.4, Compound Interest. So here are our objectives for today. We are going to learn how to use the compound interest formula, and we are going to talk just a little bit about effective annual yield and what that means, and we are going to learn to calculate present value. So let's go ahead and get started. So what is compound interest? Compound interest is interest computed on the original principal as well as any accumulated interest. And this is the reason that compound interest is so powerful. It means that the borrower is paying interest on interest. Now, if you are investing and somebody else is using your money, then that's good for you. But if you are the one borrowing money, then compound interest can actually work against you. An example of a compound interest loan would be credit cards. And y'all know how much trouble you can get into really quickly with credit cards, because what happens is you buy something on credit, and then if you don't pay off that whole amount that month, then the credit card company charges you a little interest. That's the price of using their money. And then if you don't pay it off the next month, not only do they charge you interest based on what you still owe them, but they charge you interest based on last month's interest. See, that's compound interest, and that's why it's so hard to get out of credit card debt if you ever get into it. But on the other hand, an example of a compound interest investment would be like a retirement account. So compound interest plays a big role in why some of us are able to retire with lots more money than we actually saved. What happens is you put back money, and that money earns interest, and then in all subsequent years, that interest also earns interest. That's the power of it. So this is why compound interest is so important, and we really need to take a look at it here today. So before I just throw a new formula at you, I want us to think about what we already know about simple interest, and then we will see how that applies to compound interest. So imagine this situation. We've got a principal of $1,000 and a rate of 5%. What we're going to do is first calculate the future value with simple interest at the end of 3 years. So we're just imagining that the bank is just going to pay us one interest payment at the end of 3 years. So you remember the formula that we had in the last section. Amount equals principal times parentheses 1 plus rate times time. Okay, so in this case, our principal is 1,000, our rate is 0.05, and the time is 3 years. So let's plug those values in. 1,000 times parentheses 1 plus 0.05 times 3, and that would give us an amount of $1,150 at the end of 3 years. And that's how simple interest works. Now let's look at how compound interest works. So what we're going to do here is start with the same $1,000 that we started with up here in the simple interest calculation. But what we're going to do is just calculate the interest for 1 year. And then at the end of that first year, we will add the interest earned to the $1,000. And then for the second year, we'll calculate the second year's interest based on the new total. So we will have interest that's earning interest, and then we'll do the same thing for the third year, and you'll see how that changes things a little bit. Okay, so using the same formula for future value, we'll have A equals P times parentheses 1 plus RT, and at the end of the first year, A will equal 1,000 times parentheses 1 plus 0.05 times 1, and that would give us an amount of $1,050. So at the end of the first year, we would have $1,050 in our account because they would go ahead and pay us the interest at that point, okay? And so we start year 2 with $1,050, and this year's interest payment will be calculated on a principal of not $1,000, but $1,050. So now our extra $50 of interest is also going to start earning interest. Okay, so for the second year, same interest formula, but this time the principal is $1,050 Now, the parentheses is not going to change because it's still 1 plus RT. The rate is still 5%, and the time we're leaving it in there is still just one more year. So times 1 plus RT. Now, this time I did not even write the times 1 because anything times 1 is itself. And if we're always going to use a time of 1 year, then why bother to write times 1 every time, right? So I just wrote it this way, and then let's calculate 1,050 times 1 plus 0.05, and at the end of the second year, our account will have $1,102.50. Now look at it. In the first year, we gained $50 from where we started. In the second year, we gained $52.50, right? Because if we started with this amount and we ended with this amount, you can subtract and you can see that this time we gained $52.50, so more than the $50 that we gained in the first year. We gained a little more this time. And let's go ahead and do the third year. So we start the third year with $1,102.50. That is $102.50 more than we started with at the beginning. And so now this whole $102.50 is also going to be earning interest. So same formula, and this time the principal is $1,102.50. The 1 plus RT is still the same, 1 plus 0.05, and this time we come out with a final amount of $1,157.63. Okay, now if you subtract the amount at the end of the third year from the amount at the end of the second year, you can see that this time we gained $55 plus some change. So the first year we gained $50, the second year we gained $52.50, the third year we gained $55.13. So because our interest earns interest each year, the amount of interest we earn each year also grows. And this is what makes compound interest, again, so powerful. And now I know that it's not a lot because we're working with a small amount of money and we're working with a small amount of time. But imagine if you could have several $1,000s, maybe tens of thousands of dollars or hundreds of thousands of dollars in an account, and you could leave it in there not for 3 years but for decades, maybe for somebody's whole lifetime, like a trust fund, like a baby is born and they don't get their money until they're an adult, and that money has sat in that fund for all those decades, earning interest on interest on interest. This is how investments grow like they do. So this is the power of compound interest. Let's see if we can come up with sort of a general formula so we don't have to do each individual calculation for each individual year. So I just want you to look right here. Notice that in year 2, where we used this $1,050, instead of plugging in the $1,050, what if we had plugged in the formula that we used to get the $1,050? So I'm just going to write this same thing again, but instead of $1,050, I'm going to write this expression right here, okay? So the amount in the account is equal to not 1,050, but 1,000 times this parentheses, okay? And then I multiplied by another 1 plus 0.05. So now I have two factors that are 1 plus 0.05. A better way to write this would be 1,000 times 1 plus 0.05 to the second power, right? Because if I have a factor times itself, then that's what exponents are for. Okay, now let's go to the third year. And remember this $1,102.50 that we got from the end of year 2? Okay, well that was calculated with this formula. So this time when I copy this down, instead of writing this $1,102.50, I'm going to write the expression that we used to calculate it. So I'm going to write 1,000 times 1 plus 0.05 times 1 plus 0.05, and that represents this amount. And then we had another 1 plus 0.05 factor that we multiplied in there to get our final amount. Now, what's a better way to write this? it would be 1,000 times 1 plus 0.05 to the third power, because we have 3 of these factors here. Okay, so check it out. To get the interest at the end of the first year, we did the principal times 1 plus RT. And we're basically ignoring the t because the way we're doing this, t is always 1. Okay, and then at the end of the second year, it was the principal times 1 plus r, but squared because we're at the end of the second year. And then at the end of the third year, it was principal times 1 plus r to the third power because we're at the end of the third year. So if we're compounding once a year, then we can use this formula. A will be equal to the principal times 1 plus r with an exponent of t, where t represents the number of years that we're investing, r represents the interest rate, and p represents the principal or the starting amount. And again, this formula works as long as we're compounding the interest once a year. But guess what? Interest can be compounded more than once a year. And the period of time between 2 interest payments is called the compounding period. The period of time between 2 interest payments is called the compounding period. When compound interest is paid once a year, then the compound period is 1 year, and we say that the interest is compounded annually. But if the interest is paid twice a year, then the compounding period is 6 months, and we say that the interest is compounded semi-annually. And when interest is paid 4 times a year, then the compounding period is 3 months, and we say that the interest is compounded quarterly. In general, when compound interest is paid n times per year, we say there are n compounding periods per year. So if interest is paid once a year, then we would say there's 1 compounding period, so n would equal 1. If interest is paid twice a year, then there are 2 compounding periods per year, so n would equal 2. If interest is paid every 3 months or quarterly, then it's paid 4 times a year, so n would equal 4. So you see how that works. What if they compounded daily? Then there are 365 days in a year, so n would be 365, right? That's how we figure out what n is. And now what we're going to do is take our standard formula for compound interest based on compounding once a year, and we're going to adjust it for compounding more than once a year. So what happens is that R is the annual rate, of course, and if they're going to compound more than once a year, they're not going to pay you the entire percent that R represents for just that part of a year. So if they compound twice a year, they're going to pay you half of R. If they compound 4 times a year, they're going to pay you a fourth of R in each compounding period. So that over the whole year, you get the whole thing, but you only get part of it in each compounding period. So what we do is we say that R divided by N is the rate for a partial year. And so we would fix this formula. Instead of plugging in the entire R here, we'll have to plug in R divided by N, because that's all they're going to pay you in one compounding period. Now what about T? Okay, well, if they're going to pay you more than once a year, then we have to adjust T as well, because we want this exponent to represent the number of times that they pay you interest. So the exponent would now need to show the total number of compounding periods. So instead of just T, it would be T times N, see? Or we write it NT, actually, is how you'll always see it written down. So this is going to be our new formula for compounding interest N times per year. So before we get any examples going, let's take a really good look at this formula and make sure we understand it. A still represents the future amount or the balance in the account. The P represents the principal like it always has. R is the interest rate in decimal form. And now we know that N is the number of times per year that the interest is compounded. And again, just like we saw in section 8.3, the amount A is called the account's future value, and the principal P is called the present value. Okay, now just to get a little practice with our new formula, and so that you can see the difference between different compounding periods, what we're going to do is take that same amount of money that we did a couple of slides back. So remember, we had principal equals $1,000, rate equals 5%, and we're going to go for 3 years again. But this time we're going to calculate the amount based on compounding each month, so compounding 12 times a year, and then again compounding each day, so compounding 365 times a year. So let's see how that works out. So we'll start with part A, and here is our formula. This is the same formula that we saw on the previous slide, and let's write down what we know. So we know that the rate is 5%, so in decimal form that's 0.05. We know that we're compounding each month. There are 12 months in a year, so n is 12. Remember, n is just the number of compounding periods in a year. And then we know that the time is 3 years because of the problem here. And I didn't write it, but of course the principal is $1,000. Okay, now look at your exponent here. We know that we're going to need the number n times t, so I'm going to go ahead and calculate that. N times t is 12 times 3, so that's 36. Okay, that's going to help us when we plug in our numbers. Okay, now plugging in the values that we know. A equals P, which is 1,000, times parentheses 1 plus R divided by N, so that's going to be 0.05 divided by 12, close the parentheses, and then your exponent will be N times T, which we already figured out is 36. Okay, now let's enter this in the calculator. Okay, so we have A equals 1,000, so we'll go ahead and enter that, times parentheses, so we don't even need the times button, you know, just the parentheses, 1 plus 0.05, of course, you know, we just always enter 0.05, we don't actually type that leading 0, divided by 12, so that's divided by 12. Now, I want everything in parentheses to be raised to this exponent, so I do need to close the parentheses, and then your exponent button is right here. This is the power button, so to the power 36, and then equals. And here is our final value rounded off to 2 decimal places, so we end up with $1,161.47. Now, if you remember when we did this with annual compounding, when we made that table a couple of slides back, I believe we ended up with $1,157, so not a huge difference, but just a small difference. But then again, we are working with a small amount of money and a small amount of time. Okay, now let's try it where we're compounding each day. So this time, same formula and same R, but this time, since we're compounding each day, n will be 365, because 365 days in a year. The time is still 3 years, so this time when we calculate n times t, that's going to be 365 times 3, and that's going to be 1,095. So now plugging our known values into our formula, A equals P, which we know is 1,000, times parentheses 1 plus R over N, so that's going to be 0.05 divided by 365, close parentheses, then raised to the power N times T, which we already figured out that number is 1,095. And now when you enter that expression into your calculator, you get a final amount of $1,161.82. So really not a huge difference at all, just a matter of a few cents, because we're dealing with such a small amount of money and again such a small amount of time. So I'm sure you've noticed that both examples that we've done, we have calculated n times t ahead of time, but I wanted to show you what happens if you don't calculate n times t, if you just put the numbers in the exponent together. So instead of getting the 1,095 that we calculated ahead of time, what if we just try to enter it as 365 times 3? You can do it, but you have to use the parentheses. So let me show you. If we enter 1,000 here times parentheses 1 plus 0.05 divided by 365 and close the parentheses. Now, whatever I enter next, the calculator will consider the exponent. So if I go power 365 times 3, The calculator only thinks that the 365 is the exponent, and then it thinks I want that whole answer multiplied by 3. And so when we press equal, notice how we do not get the right answer. We get like triple the answer, almost. So this is not the way to do it. But if you do want to enter the numbers for n times t instead of calculating it ahead of time, here's what you do. 1,000 times parentheses 1 plus 0.05 over 365. When you get ready to enter your exponent, just put the whole thing in parentheses. So power parentheses 365 times 3, that solves the problem, and we get the correct answer. And let me show you even another way to do it using the answer function on your calculator. So what we could do is calculate 365 times 3, and after we press equal, that 1095 is saved as the last answer. So now let's enter the rest of our expression. And now that we're ready to enter the exponent, we hit that power button, but we remember that our exponent is stored as the last answer. So now we use second answer and press equal, and there is yet another way to get the correct answer without having to use an extra set of parentheses just for the exponent. Okay, so here's example 1, and we're just going to practice using our same formula that we've been working with, our compound interest formula. And it says you deposit $2,000 in a savings account at Hometown Bank, which has a rate of 1.6%. Interest is compounded annually. Okay, so part A says find the amount A of money in the account after 3 years. So A, of course, is the future value. It's the amount that we will have at the end of 3 years. And so let's get our formula written down. We know that A is equal to P times parentheses 1 plus R over N, close parentheses, raised to the N times T power. Now from the problem we know that P equals 2,000. Let's go ahead and write down our interest rate and convert that to decimal form. So if the interest rate is 1.6%, then in decimal form, when we move the decimal back 2 places to remove the percent symbol, our R is then 0.016. If they compound the interest annually, then they compound once a year, and so N is 1. And they said to find the amount in the account after 3 years, so T is 3. And now let's go ahead and calculate N times T. So N times T would be 1 times 3, or I wrote 3 times 1, and of course that's 3. Okay, now plugging our known values into our formula, A equals P, which is 2,000, times parentheses 1 plus R divided by N, so 0.016 divided by 1, close parentheses, then the exponent is NT, which we know is 3. Okay, entering all of that into the calculator, we are going to get a final amount of $2,097.54 at the end of the 3rd year. Okay, I know that you've got this probably, but I did want to point out, because sometimes people don't realize, if you're just dividing by 1, then you don't really have to type that in. So when we type this in, of course, we're going to have our 2,000 times parentheses 1 plus 0.016, and I don't have to type divided by 1. So I could do that, close the parentheses, and then my power. And that's all there is to that. And then part B says find the interest. Okay, at the end of the 3rd year, if we finish with $2,097.54, but we only deposited $2,000, then the difference between those two is the interest. So interest equals A minus P, and so that would be $2,097.54 minus 2,000. So we earned $97.54 in interest just for letting our money sit there in the bank. Okay, example 2. You deposit $7,500 in a savings account that has a rate of 1.2%. The interest is compounded monthly. How much money will you have after 5 years? Okay, again, we are going to start by writing down our formula, and then we can see that the principal is $7,500. Let's go ahead and write down our interest rate, because we have to convert this to decimal form. So when we move the decimal back 2 places, we're going to have r equals 0.012. And we know that the interest is being compounded monthly. So there are 12 months in a year. So that means that there are 12 compounding periods in a year. And so n is 12. And the time is 5 years. That was stated in the problem. And since we have both of these numbers here, let's go ahead and calculate our exponent, which is n times t. So that would be 12 times 5, which is 60. Okay, now plugging all of our known values into our formula, we would have A equals P, which is principal, which is $7,500, times parentheses 1 plus R over N, so 0.012, divided by 12, to the exponent NT, and N times T we already know is 60. Okay, putting all of this in the calculator, we are going to get a final value of A equals $7,963.54. And then part B says find the interest after 5 years. And we know that interest is the difference between the final amount and the principal, so we will subtract $7,963.54 minus $7,500, and then we'll see that interest equals $463.54. And here is example 3. Now, if you want to pause the video and try this on your own, I think that's a great idea. And now I'm going to go through this problem with you. So it says you deposit $4,200 in an account that has a rate of 1.6%. The interest is compounded quarterly. How much money will you have after 10 years? Okay, let's go ahead and write down our formula. And we can see that the principal is $4,200. We can see that the rate is 1.6%. When we convert that to decimal form, we'll have 0.016. Then we want to get the exponent n times t. So if we're compounding interest quarterly, then we're compounding interest 4 times a year. So that would mean n equals 4. And t is given in the problem as 10 years. And so n times t is going to be 4 times 10, which is 40. Okay, now plugging our known values into our formula, A equals principal, which is 4,200, times parentheses 1 plus R over N, so that's going to be 0.016 divided by 4, close the parentheses, and then your exponent is N times T, which is 40. And when you enter all that into the calculator, you get a future value of $4,927.17. And then for part B, find the interest after 10 years. We will just take our future value minus our principal, and that will be $4,927.17 minus $4,200 for an interest amount of $727.17. Okay, now in example 4, we're going to compare 2 different investments. So it says, suppose you have $30,000 to invest over 20 years. Which investment yields the greater return? Would you rather have 4.15% compounded semi-annually, that's twice a year, or would you rather have 4.1% compounded weekly? So the first one has a little better interest rate, but the second one has more compounding periods per year, so 52 compounding periods here compared to only 2 in the first investment. So would it be worth it to go with the lower interest rate if you could have more compounding periods? Well, that's what we're going to find out. So let's just take our formula here. It's the same formula we've been using, and we'll just use it in both situations. So for the first one, of course, principal for both is $30,000, but in the first one, R is 4.15%. In decimal form, that's 0.0415. The N is 2, because if we compound semi-annually, that's twice a year. So N will be 2, and the time is 20 years. So that means that N times T is going to be 2 times 20, which of course is 40. And now plugging our known values into our formula, we'll have A equals P, which is 30,000, times parentheses 1 plus R over N, so 0.0415 divided by N, which is 2, close the parentheses, and then the exponent is going to be N times T, which is 40. When we enter this in the calculator, we get a future value of $68,217.66. And then for the second investment, R is now just 4.1%, so in decimal form that will be 0.041. But now we're compounding weekly, so there are 52 weeks in a year, so N will be 52. And since our time is 20 years, N times T will be 52 times 20, which is 1,040. Okay, now plugging our known values into our formula, A equals P, which is 30,000, times parentheses 1 plus 0.041 divided by N, which is 52, close the parentheses, and then the exponent here is 1,040. And when we evaluate that on the calculator, we get a future value of $68,092.99. So again, it's not a huge difference, but we did come out a little bit ahead with the interest rate of 4.15% compounded semi-annually. So the question becomes, is there a better way to compare investments? Or do we have to do two big long calculations every time like we did on the last slide? Well, the answer is yes, there is a better way to compare investments. And it's something that banks call effective annual yield. If you're making an investment, it's called effective annual yield. If you're taking out a loan, they call it effective annual rate. But it's just two different terms for the same thing, depending on whether you're doing the investing or the borrowing. Basically, what it is, it's a way to calculate what the interest rate would be to get the same total amount without compounding. In other words, it's a way to figure out what simple interest rate it would take to get the same future value on a certain amount of principal. Now, if you are investing money, then a higher effective annual yield is better. Higher is better if you're doing the investing because you want to be paid more money. So you want to get paid at a higher rate. That's if you're investing. But if you're a borrower, if you're getting a credit card or something, you want a lower effective annual rate. That will be better because then you will pay less money with the lower rate. Okay, so here is our formula for effective annual yield. Let's read about it. It says, suppose that an investment has a nominal interest rate R. So in other words, that's the compound interest rate, the one that they tell you. So it has a nominal interest rate R in decimal form. So we've converted our R to decimal form. And the account pays interest in times per year, just like we're used to. Then that investment's effective annual yield, Y, in decimal form is given by this formula. It's parentheses 1 plus R over N, close parentheses, raised to the power N, and then subtract 1. And of course, this, what you've calculated here, will be an interest rate. And it's the equivalent simple interest rate that you would need to get the same amount of money based on this rate and this number of compounding periods. So it's going to come out in decimal form, and what you're going to have to do then is just convert it to a percent. So move the decimal 2 places to the right and put your percent symbol on there. Let's get a little example here. So this is example 5. It says an account has a nominal rate of 2.5%. The interest is compounded quarterly. Find the account's effective annual yield. Notice that in order to calculate effective annual yield, we don't need to know the principal, P, and we don't need to know the amount of time that the investment is being left to sit in the bank, because neither one of those things has anything to do with how good the investment is. All we want to do to compare apples to apples is figure out what simple interest rate it would take to get the same amount of money based on a compound interest rate of 2.5% and 4 compounding periods per year. Okay, so let's go ahead and write down our formula for effective annual yield. we know that y equals, parentheses, 1 plus r over n, close parentheses, all raised to the n power, minus 1. And so we're going to need our r and our n. So from the problem, we know that r is 2.5%. In decimal form, that would be 0.025. And then they told us that interest is compounded quarterly, so that's 4 times a year, and so n is 4. And now let's plug those values into our formula. So we'll have open parentheses, 1 plus r over n, so that's 0.025 divided by 4, all to the 4th power, and then minus 1. Let's take a look at that on the calculator. So we'll start with our open parentheses, 1 plus 0.025 divided by 4, close parentheses, exponent is 4, so power button 4, and then if the next thing I enter is minus 1, the calculator will know that the exponent is just 4 and that it's supposed to do that whole calculation first and then subtract 1 from the result. So there is our y. And so here is the interest rate that we got from the calculator, and now we need to convert this to percent. So we move the decimal 2 places to the right and put the percent symbol on it, and it's 2.52%. So what we just found out is that for an interest rate of 2.5% compounded 4 times a year, that amount of money that you would have at the end of 1 year is the same as if you had a simple interest rate of 2.52%. So basically it takes these two numbers and it combines them into one interest rate that you can use to compare different investments. Okay, here's example 6, and we'll get to compare a couple of different investments here. So this says a bank offers a money market account paying 4.5% interest compounded semi-annually, and a competing bank offers a money market account paying 4.4% interest compounded daily. So it's kind of the same situation we had a couple of slides back. This second account does not have quite as good of an interest rate, but it does offer daily compounding instead of just twice a year. So 365 compounding periods a year instead of just 2. And the question is, which account is the better investment? So what we'll do is we'll calculate the effective annual yield for each one, and then because it's an investment, a higher interest rate is better for us, so the one that has the higher effective annual yield will be the better investment. Okay, so here's our effective annual yield formula, and the first account has a 4.5% interest rate, so in decimal form its R is 0.045, and this one compounds semi-annually, so that's twice a year. So for this one, n equals 2. And let's go ahead and plug those values into our formula. Y then equals 1 plus r over n, so 0.045 divided by 2, then to the power 2, and then subtract 1 from that. Then entering all of that into the calculator, I got 0.0455. And then converting this to percent, of course, we move the decimal 2 places to the right, and that's 4.55%. For the other account, we know that R equals 4.4%, so in decimal form that is 0.044. And we know that this one compounds daily, so how many compounding periods are there in a year? Well, 365 days in a year, so n equals 365. And then in our formula, y equals parentheses 1 plus r over n, so 1 plus 0.044 divided by 365 to the power 365, and then minus 1. Okay, so here's what I got on the calculator, and I've copied down an extra digit here just to show you something. So if we want to round this one off to match the first one that we did, notice that here I kept 4 decimal places, 1, 2, 3, 4. So over here, if I want to keep 4, then the last one would be the 9, and I would look at the 7 then to decide if this stays a 9 or gets rounded up. Of course, the 7 is big enough, so the 9 is going to need to be rounded up, so the 9 will change to a 0, but just like when your odometer rolls over on your car, if the 9 changes to a 0, the 4 will change to a 5. So I'll get 0.0450. And then when we convert this to percent, we'll get 4.50%. Okay, now comparing these two effective annual yields, the first one was 4.55% and the second one was 4.50%. And it's probably not that huge of a difference, but this first one does pay a little better. It has a little better interest rate. And since we're investing, we want the highest interest rate we can get. So we would probably pick this first one. Now let's talk about present value. So you remember in 8.3 how we had those problems where they told us how much money we wanted to end with, and we had to figure out how much money we needed to start with. Okay, that's what we're doing here. So we are calculating present value. So it says, suppose that you know how much money you want to have at the end of an investment period, but you need to know how much you should start with in order to reach that goal. So let's take a look at our old future value formula. This is the formula we've been using, but now we want to solve it for P. So we want to isolate the P. So what we would do in algebra is we would divide both sides by whatever this number is. So I'm going to divide the whole right side by that parentheses with its exponent. So that's going to isolate the P, but I need to do it to both sides. Okay, so it cancels out from the right. So now I've got P equals A divided by that same parentheses with that same exponent. And this is the present value formula. So here it is again. If A dollars are to be accumulated in T years in an account that pays rate R compounded N times a year, so all those variables do the same thing that we're used to, then the present value, P, that needs to be invested now is given by this formula. And we have to remember that whether the number we get should be rounded up or not, we are always going to round up. So remember to round the principal up to the nearest cent or the nearest dollar if the instructions say nearest dollar. So round up when computing present value so that there will be enough money to meet future goals. So here is a little example for us, and this is example 7. It says how much money should be deposited today in an account that earns 6% compounded monthly so that it will accumulate to $20,000 in 5 years. Okay, so we want the future value to be $20,000, and we are trying to calculate how much money we need today. So that's present value. So let's go ahead and write down our present value formula, and then we'll pull out each of the numbers that we need. We know that the future value needs to be $20,000. We know that the rate is 6%, so in decimal form that's 0.06. We know that the interest is compounded monthly, so there are 12 months in a year, so that means N equals 12. And we know that we're leaving the investment in there for 5 years, so T equals 5. Okay, now we know that N times T is our exponent, so let's go ahead and calculate N times T. So that would be 12 times 5, so that's 60. And now let's plug each of our known values into our formula. So P equals A, which is 20,000, all divided by parentheses 1 plus R over N, which is 0.06 divided by 12, close parentheses, to the power 60. Okay, so even though this one looks really complicated on the calculator, it could not be easier. So it's just 20,000 divided by, and we want to divide by this whole thing. So parentheses 1 plus 0.06 divided by 12, close your parentheses, and then the exponent needs to be 60. So power 60 equals, and there it is. And here's the number we got from the calculator. Now, we know that when we calculate present value, we always round up. So even though this next decimal place is not large enough to cause me to round up according to the rounding rules, we always round up anyway. So this 4 is going to change to a 5, and our present value that we invest to achieve $20,000 in 5 years would need to be $14,827.45. And here is example 7 part B. It says parents wish to have $80,000 available for a child's education. If the child is now 5 years old, how much money must be set aside at 6% compounded semi-annually to meet their financial goal when the child is 18? So we're trying to figure out how much we need to invest now. That means we're trying to find a present value. So we want the present value formula. And let's go ahead and get our values that we know from the problem. We know that the future value needs to be 80,000, so A equals 80,000. We know that the interest rate is 6%, so in decimal form that's 0.06. And we know that the interest is compounded semi-annually, so that means it's compounded twice a year, so we know that N equals 2. And now for the time, the child is already 5 years old, and we're going to need the money when they turn 18. So 18 minus 5 means we can leave the money invested for 13 years. Okay, now we know that our exponent in our formula is going to be N times T, so let's go ahead and calculate that. N times T would be 2 times 13, which is 26. And now let's plug our known values into our formula. So P equals A, which is 80,000, all divided by parentheses 1 plus R over N, so that's going to be 0.06 divided by 2, close parentheses, to the 26th power. And entering all of that into the calculator, I got 37,095.5782. And let's say that we want to round off to 2 decimal places because we're dealing with money. So normally we would look at the third decimal place and decide if this stays a 7 or goes an 8. But remember, we are calculating present value, so we will always round up when we're calculating present value. So this becomes an 8 anyway, regardless of what this next digit is. And we would need to invest $37,095.58 to end up with $80,000 given these other values. Okay, you guys, that is it for section 8.4. I hope this has been a good one for you, and I will catch you in our next video, which is going to be section 11.1, and we're going to start working with probability. See you then.